Section 4.3 is scientific notation. So essentially for what scientific notation is, it's a way that allows us to write really, really, really large numbers or really, really small numbers in this compact notation. So a number is written in scientific notation when it's expressed in this form: a times 10 to the nth power. So something times 10 to another power. So the absolute value of a, the a out front, is going to be greater than or equal to 1 and less than 10. So that's pretty important. And then the n is an integer, meaning it's a positive or negative whole number. So for example, something like, let's say we had 9,630,000. In scientific notation, this would be 9.63 times 10 to the 6th power. And then I'll explain how we go back and forth between the two. So you can probably see how if the number was even bigger than that, then it's nice to have it in that compact notation. So let's go from scientific notation to decimal notation first. So decimal notation is just kind of our normal expanded out number. So when we're starting in scientific notation, it's going to be a times 10 to a number. If the n is positive, so if the exponent's positive, we're going to move the decimal point to the right n number of places. If the n is negative, we're going to move the decimal point to the left n number of places. So let's do this first example here. So we have 6.2 times 10 to the 7th. Okay, so this essentially means 6.2 times 10 million. 10 to the 7th is 10 million if you expanded it out. So what we're going to do is, I'm going to start with, I'll write it down here. We're going to start with 6.2. We're going to take that decimal, and the 7 is positive, so we're going to move it to the right 7 places. 1, 2, 3, 4, 5, 6, and 7, and put it right here. All of those empty little divots there that I have, we have to put a 0. So that's going to be our number. It's going to be 62 million. So 6.2 times 10 to the 7th is just 62 million. And then obviously we don't need that decimal at the end for this. Next one, negative 2.019 times 10 to the negative 3. So I'm going to ignore that negative for a second, and I'm just going to know that our answer is going to be negative. So the exponent here is negative. It's negative 3, so it's going to be moving this decimal point to the left 3 spots. So it's going to be right there. Once again, we have to fill in some zeros here. So our answer is going to be 0.002019. I'm just going to put a 0 in front of the decimal. 0.002019. And we can't forget that it is negative. So that's just the negative that was originally out front. Okay, so it's just as easy when it's in scientific notation switching to decimal form, which is just kind of a regular number form. It's just as easy as moving the decimal over to the left or to the right. So let's go the other way now. Let's convert from decimal notation to scientific notation. So to write this in scientific notation, we have to determine what the a and the n are for the number out front and then the exponent. So to determine a, we move the decimal point in the given number, in the number that we have, to obtain until we get a number between 1 and 10. So we're going to start with the number. We're going to move that decimal over as far as we have to until we get a number whose absolute value is between 1 and 10. It's including the 1 but not including the 10. So essentially what we're trying to do is we're trying to get a single digit number. Then we're going to determine n by counting how many places the decimal point was moved over. If it's positive, or it is positive if the decimal point was moved to the left, and it's negative if it was moved to the right. So let's see an example here. not as confusing as those instructions make it seem. So we have 34,970,000,000. So the decimal point is all the way over here, right? If it's not written, it's at the end of the number. So we have to continue to move it until we get right here. Once we get right there, we get to 3.497. We can stop right there because the rest are zeros. And it's going to be times 10. Now we have to determine how many spaces we moved it over. So we moved it to the left. It looks like 10 spots. And it's going to be positive because we moved it originally to the left. So it's the opposite way of thinking from doing it on the previous page. So this is going to be 3.497 times 10 to the 10th. So just make sure that it kind of makes sense here. 3.497 times 10 to the 10th, starting with our answer. That means we would be moving the decimal point to the right 10 units, which seems like it's correct. So next one, we have negative 970 million. So starting with the decimal point over here on the right, we move it over until we get to right here. So this is going to be negative 9.7. So once again, we made sure we got to a single digit number. So the 9 is single digit. Times 10. And then we moved it to the left. We know it's going to be a positive exponent. We have to count how many spots we moved it over. 1, 2, 3, 4, 5, 6, 7, 8 it looks like. So it's going to be negative 9.7 times 10 to the 8th. Last one here for this example. So we have point, a lot of zeros. Not even going to read it. Point, a lot of zeros, and then A2. Okay, so we find our decimal, which is right here. It's over here this time. So we're going to take it and we're going to move it until we get to a number whose absolute value is between 1 and 10. So we get to 8.2. 8.2 times 10 to something. So we count the number of decimals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's going to be the negative 11th because we moved it to the right. And we should start with our answer here and think backwards to make sure it makes sense. 8.2 times 10 to the negative 11, we would be moving it to the left 11 places, which agrees with what we had. Okay, for this last thing that we have here is multiplying and dividing with scientific notation. So it's not too bad. There is a little bit of a trick that I'll mention in this first one. So what we have to do is we actually have to use the product and quotient rule for exponents. So we'll see what I mean in a second here. So let's do this first example with multiplying. We have 7 times 10 to the 3rd times 5 times 10 to the 4th. So what we can do here is what we're going to do is we're going to multiply the first numbers for each set and then multiply that power of 10 together for each set. So first we're going to do 7 times 5 and then multiply 10 cubed times 10 to the 4th. So if you got really stuck with these, you can just remember that 10 cubed is 1,000, 10 to the 4th is 10,000. So you'd be multiplying 1,000 times 10,000 times 7 times 5, and then you would have to put that back into scientific notation. So that's obviously more complicated, so we're doing it this way. So 7 times 5 is 35, and now I'm going to write it back in scientific notation. It's 35 times 10, so now we have to think, what's that new exponent? So we have the same bases and we're multiplying, so we have to add the exponents. So 3 plus 4. So we get 35 times 10 to the 7th, but we're not done yet. We need that 35 to be a number between the absolute value of the number, to be between 1 and 10, because we need it to be a single digit out front. So it's going to be, we want it to be 3.5 instead, because 3 is a single digit. 35 was a double digit. So we have to adjust the exponent though, because we moved that over. Since we moved that one more spot to the left, we have to add 1 to the exponent and make it 8. Okay, so you can double check to make sure that that's correct, that you can make sure that 3.5 times 10 to the 8th is the same as 35 times 10 to the 7th by putting them both in decimal form if you wanted to, but that's a little bit tricky for that one. I'm just going to make a little bit of a note over here and say that 7 times 10 to the 3rd times 5 times 10 to the 4th, it's the same as 7,000, so this is them in decimal form, times 50,000, which would be the same as 3, 5, 1, 2, 3, 1, 2, 3, 4 with that many zeros, so that looks like 350 million. And then you could convert that to scientific notation and you'd end up getting the same answer, 3.5 times 10 to the 8th. Okay, so doing one more here with dividing. So it's 4 times 10 to the negative 5 divided by 2 times 10 to the 3rd. So for these ones, it's similar to what we just did. We're going to divide, in this case, the numbers out front, and then combine the 10, the power of 10s, using the quotient rule in this case. So 4 divided by 2 is 2. Make a little note that that's what I did here. And then it's going to be 2 times 10. So we subtract the exponents. Negative 5 minus 3. So this is 2 times 10 to the negative 8. So that one's actually done. The 2 is a single digit number. So we're done. We don't have to adjust it at all. Okay, so that's it for section 4.3.